So let's see what this looks like in the form of a problem. Here's one taken out of a textbook, and I want you to see what it normally looks like. These types of problems when they're not using the shortcut. What you can see here, you can see the rice. That's the first thing. That's typical how these are worked. Okay, so let's kind of dissect this one. What is the pH? So already let's think about that. So what do we need? We want pH, which we know is equal to minus log of H plus. Okay, that's probably going to be our target right there, but we'll see. Okay, what is the pH of a 0.1 molar? And this is a weak acid. Why? Because it's not one of your 7 strong acids. So we know right away we have a weak acid system. Okay, for this particular acid it gives Ka, so we know Ka. So what is the pH? Well, how are we going to work that? So let's see. We know for a weak acid, we know that H plus is equal to this shortcut. But wait, the problem, the way they work it in the book is not going to be the shortcut. So let's see how they do it. The first thing they do is Ka is given. So you know there's a Ka for this equation at equilibrium. And they write it down as products divided by reactants. And the concentrations you don't know, use the rice. And X winds up being the H plus concentration. So you have H. You have x squared divided by 1 minus x. And here's the decision point right here. Does the shortcut work or not? Here, they're kind of making this assumption here. And so thus we can assume, so they're kind of thinking through all of that. So once they do that, notice that they did take the shortcut. They dropped x off, and it's just 0.1. Okay, and now they merely solved for x because we know x is also equal to H plus concentration. Okay, the original question asked for a lot of other things, and I'm just illustrating with this. So basically you can take this and do the minus log of that, and you get the pH. Does it test your answer? Does it make sense? Sure, this is a weak acid, and I would expect the pH to be less than 7, at least that. Okay, what if we just went straight and did the shortcut? If you didn't do all of that, you would immediately say weak acid. You would default over to that. And then since you're looking for H plus, you would just plug this in, right? 0.10, your Ca. And your Ka is 3.5 times 10 to the minus 8th. And you're just going to take your square root of that immediately, and you're going to get H plus. And then you're going to take the minus log of that, and then you've got your answer. So you can work through this every time, but what you're going to do is wind up with Ka, and this kind of takes you straight to the end of the game. To remind you right here, I didn't work this out because that's a given. That's one of these that you're supposed to already know and be really familiar with how to do. Okay, let's work another one. Here's one, there's another weak acid system. We can see chloroacetic acid is indeed a weak acid system. And so let's just analyze this. The pH, so we know the pH of this system, which is equal to minus log of H plus. And I like this because I have two things that's on my little square that I use. Minus H plus, I know it's a weak acid. What does that bring to mind immediately, whether I use it or not? It reminds me of this. Okay, I'm liking this because right now I can already see I've got relationships between different things, and my guess is this is not going to be a very hard problem because of that. Okay, and the pH is equal to 1.92. Well, that's kind of nice. I know right now I can get the H plus concentration. Very, very easy. So, what are you looking for? Well, let's see. We're looking for this, so this should be a pretty darned easy problem. Let's do the analysis of it before we do it. Do we know H plus? Nope. But can I calculate it? Yep, so that's one of those check plus things. I don't know it, but I could get it. Do I know Ca? Yep, that's given. Ka, just a very simple matter of solving this. So let me continue with the problem and just show you what we just did. Without plugging the numbers in, we rearranged this and solved for K, and then we took the minus log of this. And we took the minus log of this, and that gave us a calculated pKa. Now, that did not take long to do at all, but I want to now compare that and contrast it to what the textbook did, which is use the traditional rice. Now, here's a situation in which they looked at the value from pH. They calculate the log of H+, so we know the log of H+, yes. We know the log. We know the concentration of H+, and we know the concentration of Ca, and we can literally do our test now. We can do our test. So Ca is going to have to be much greater than 20 times that for our assumption to be true, or else this is too large. And you can see that it fails the test. So, in other words, this is large enough. This X value is large enough so that it can't be ignored. You have to do the quadratic. Or do you have to do the quadratic? And here's where it gets into, do I really want the correct answer? Am I doing research? Or do I just want to get the answer on the test right? Which normally, if you're taking a test, it's just the latter. So let me show you what I normally do. If I see the answers are very close, 2.84, 2.85, 2.86, 2.87, I can see they're varying in the second decimal place. And so I'm going to need to have a lot of precision, and I'm going to go ahead and say, oh my gosh, it fails, I'm going to do the quadratic. But if your answers are very far apart, let's say the answers are 2.85 and 3.7 and 8.4 and 0.2, they're very far apart. So you know good and well 2.9 is going to match up with 2.85. That is much closer to 2.85 than anything else. So in that case, if the numbers were spread out in my answer choices, then I would just use the shortcut and save a lot of time. If the answers are very tight and you fail this test, then you have to do the quadratic. But don't just by default, if it fails, automatically go through the quadratic. Kind of do your analysis of your test and think through these, and I think it might help you out. Anyway, my default is to just do this real quickly and look and see if an answer is pretty close to it. Right. Hope that helps. Okay, percent ionization. This is what you're doing. There's nothing particularly difficult or challenging about this, except the way that it's worded. You just need to know the definition of percent ionization, and that is the amount of hydroxide concentration at equilibrium over the initial concentration. That's it. So what you do is you take these problems, and it seems really complicated when you do percent ionization. Don't. Just use your regular formulas to calculate H+, and use your regular formulas to calculate or your problem to see if Ca is given, and then just plug them into this equation. So let's see what one of those looks like. Calculate percent ionization for a weak acid. Okay, calculate the pH. Okay, so now we know we have the pH. And percent ionization for a 0.1 molar of acetic acid. Okay, so we're given a Ka, we know acetic acid is a weak acid, and we're given a Ca. So we're given a Ca, we're given a Ka, and we know it's a weak acid. Well, this is kind of a duh, right? Okay, already, you know your formula for that. If the shortcut holds, okay, is this. And we know this, and we know this, and we can calculate this. So indeed, I go through the process there of doing that and calculating that, and then taking the minus log, because it asks for pH, and that's 2.87. So how do you get percent ionization? Well, percent of anything is part over the whole. Well, what's the part? The part of this that ionized. Well, what is that? Well, the part that ionized is the same thing as the H+ concentration. That's really the only trick, is to realize that. It's ionized. Well, that's what it means. It formed the ions there. And so the ion that it formed is an H+. So H+ is the proxy for your percent ionization. That's the trick. So now it's just asking you, what's the H+ concentration? Oh, I know, I've already used it. What's Ca? Oh, I know that was given. Okay, so don't sweat these percent ionization. Just do them normally, but you do need to remember the formula there of percent ionized is equal to whatever the concentration of your ion is in an acid base. It's going to be a proton or a hydroxide group, and the initial concentration is going to be Ca or Cb. Boom, that divided by that times 100, and it's 1.3. Fairly straightforward. Don't make it harder than it already is. Okay, let's talk about the relationship between Ka, Kb, and Kw. This is another one of those formulas you want to keep in your repertoire because it is very, very useful. Because what this means is you're always going to know Kw, right? That's what? 10 to the minus 14th? You kind of got that one down. What this means is if you know Ka, then you know Kb. Or if you know Kb, then you can calculate Ka. And this is common fare on chemistry test. To give you the Ka for an acid and then to ask you about its conjugate base. Not a problem. You just need to know to do that. Okay, very, very simple stuff. So just remember to use this formula. Okay, take a quick aside and let's look at the relative strengths of conjugate acid and conjugate base. This is kind of going to make sense. Should. If something is a really strong acid, its conjugate base is going to be really weak. If something is a really weak acid, then the conjugate base is going to be relatively strong. And so they are inversely proportional. And so let's show you some examples of that on the next page. So notice how this table is arranged is it's showing you, and this is out of your textbook, I think. Perchloric acid, okay, we know that's one of your strong acids. So since that's a strong acid, we know perchlorate ion is going to be a weak base. So as acidity, as the acid strength increases, the corresponding conjugate base strength decreases. And this makes sense. You can't have a strong acid and its anion be a strong base. Because a strong base means it wants the proton. It wants the proton. And if it gets the proton, then it's an acid. I don't know if that makes sense, but it actually makes sense to me. Okay, so now you get to things that are extremely, extremely, extremely weak acids. That means this methide ion is an extremely strong base. And this is used a lot in chemistry. We make these methide ions and they are really, really, really reactive. Okay, notice lithium aluminum hydride. We talked about hydride before. Wow. So this is taking hydrogen, which is a very, very weak acid. And so that means this is a very, very strong base. And these are the type of things that you can really kick some reactions off, the type of stuff that explosions are made out of. Why? Because these are extremely strong bases, because methane is a very stable molecule, so it's very weak. Does it actually want to lose a proton? It's very hard to get it to lose a proton. And when you do, the base that you produce is so basic, it's going to react with something trying to get rid of that charge. So it's just a good trend to know. So let me give you the relationship now between Ka and Kb. So what this means is, so you need to know that the Kb is the conjugate base reacting with water to do that. So it's these two right here. This Ka times this Kb is equal to Kw. Yes? So if you know either one of these, you can calculate the other and then use it to work whatever problem you're given.